different detectors that actually working on the different wavelength regions other than the visible or the optical light. And this video will be short, in about 5 to 10 minutes. Okay. So first one is actually the special type of, I think, special design of the detector called microchannel array. Okay. So using the microchannel array, so this is actually the anode, the microchannel array. So it is called MAMA. Okay. So the reason that actually this microchannel array is needed is the CCDs have the metal oxide. These photosensitive layers are only sensitive to the optical visible the wavelength light. Okay, so when you actually shine the UV or the infrared light onto the CCD is not responding because the photosensitive layer is not responsive to that particular the wavelengths, the photons. Okay, then how do you actually do? We are actually creating like a curved honeycomb like microchannel array made of the metal, okay, some sort of metal alloy. And this curved entrance ensure that actually incident light is hitting the wall at least once. And because the incident light is actually now the producing photoelectrons, sometimes the fast moving, especially in the X-ray and then UV range, that actually the photoelectrons actually have high kinetic energy. So the created fast moving electrons actually hit another wall, producing more the collisionally the ionized electrons. And these electrons actually, again, that actually produce more electrons. So when the single high energetic photons actually coming into the small microchannel, at the exit, you actually see like the greatly many number of photoelectrons. Sometimes depends on the design and the need. Sometimes actually one electron produce million the daughter electrons. Then these electrons are being read out in a similar way that actually in the CCD operation. Okay? So these structure is actually is ensuring that actually that the collisional cascade and the collisional the ionization is actually happening. So these actually are the types of material that actually you can create for this microchannel is far, I think you have much more freedom than selecting right combination of photosensitive layer. In fact, actually that the photosensitive layer that actually suitable for the high energy is actually pretty much non-existent. Remember that actually X-ray can actually penetrate good amount of materials. Then small layers of photosensitive layer can be basically transparent to the higher energy, the photons. Then the type of interesting detector is intensified CCDs. So this is actually not used in the real astronomical setup. This is mostly for the military, the use case. So think about the night vision goggle. One photons from the really faint object are actually greatly magnified, sometimes 10 to the 4 or like tens of million times. So producing one photon, actually they end up actually creating billions of electrons. How do you do? Entrance is the same thing. The regular CCD, photosensitive layer, that produced the photoelectrons are actually going into the microchannel, the plate. Okay? Then the series of, I think, the great number of the collisionally created electrons are actually now they produced at the end of the microchannel plate. Then this microchannel plate are actually just re-imaged through the lens and then subject to the CCD readout channel. Okay? Because of this intensification, the process, the signal to noise ratio is always worse, okay, than the original input data. but you can actually see the faint object, and then you can actually see the 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 background, and then the really faint object in I think good or the sensitivity. So think about the night vision goggle. When you actually see the night vision goggle on the background, even for the surface of the bright object are actually all twinkling, and then the fluctuating noise source, that's actually showing the decreased the signal to noise ratio, even for the case of actually well lit identified the bright object. Then this infrared array. So this is actually the oftentimes infrared arrays are actually even among the astronomers are actually that fundamental difference between the infrared array and then CCDs are not well respected or recognized. The infrared array is actually basically using the different photosensitive layers. Okay? So instead of the metal oxide, the metal oxide for I think that are sensitive to the visible optical wavelength light, we are using two different the alloys or the chemical compound. The first one is the indium antimonide, so known as the INSB, or the materials. INSB array is actually sensitive to the near-infrared photons ranging between 1 and then about 5.5 microns. And then another the common materials that are actually used in the infrared array is mercury, cadmium, and telluride. So it's actually MOCAD, the array, MOCAD materials. This is actually sensitive between the 1 to about mid-infrared 12 micron to the photons. So these are the surface photosensitive layers for the infrared photons. Then these produced infrared, I think the photoelectrons are read out per pixel without any charge transfer. Why? Because the infrared arrays are actually operating to the lower energy flux. When you actually just move the charge transfer multiple times, the photon sensitive layers are actually producing lots of dark current and then noise sources. So you want to actually read out each individual pixel by pixel without actually moving the charges to the adjacent successive charge transfer. Okay? So that means in compared to the CCD, which you have to actually have multiple charge transfer through the readout operation, this infrared array, oftentimes known as the CMOS array. CMOS is complementary metal oxide semiconductor, which is actually behind each pixel. Each pixel is producing infrared photoelectrons by using this infrared the sensitive the layers. Then the produced photoelectrons are actually being read out per pixel by its own complementary metal oxide semiconductor. So in infrared array, each pixel has its own readout channel. Okay? Because of this, there is a great interesting characteristics of infrared array compared to the CCD is actually happening. First layer, this is the photosensitive layer. Okay? Photosensitive layer, and that's the photosensitive layer, and the bottom right below is the readout due to the CMOS layer. While these top photosensitive layers are actually constantly being exposed and then producing the photoelectrons, these produced photoelectrons can be independently read out by the bottom readout the channel. So meaning that actually while the exposure is still ongoing, you can actually still reading the accumulated photoelectrons. So this is actually known as the non-destructive readout. CCD, once you actually begin this readout operation, you cannot actually expose anymore, right? If you expose, then just whole reading out scheme is messed up. But the infrared array, because there actually there's a two separate layer, photosensitive layer, readout layer is independent, and then each pixel has the readout, the method, its own readout, the channel. The infrared array, while it's actually being exposed, you can actually read out multiple times as you need it. Okay, so because of this individual pixel, the related readout, the mechanism, there's no dead column, there's no spillover, no blooming. Okay, so because of the non-destructive readout, there can be many different clever way of actually just reading out, which I will actually show the explain a little bit more. And being infrared, okay, the infrared arrays and the photosensitive layers are actually sensitive to the temperature. Okay, so that actually that it generally produce higher background the noise, the sources. That means actually that overall the saturation is actually happening faster than CCD. So without actually being saturated, but while they're actually still accumulating photons from your faint, the astronomical object, you need to actually break up the observation into the various series of short exposure. So later there are actually series of short exposure below the level of saturation limit because of the bright background, the light is known as co-ed, which we will learn about more, I think, the great details about this infrared observation mode during the infrared array lecture. And infrared arrays are actually typically have worse linearity, the relationship, so that actually you have to actually settle the below maybe that unbearable amount of nonlinearity compared to the CCD, maybe below 10% of the nonlinearity is okay. Then by using the nonlinear response, like instead of the straight line on this curve, you have to actually just from the detected signal to the true source intensity, you have to actually get the source intensity by using the sensitivity or the curve. Right? And dark current, because they're actually infrared array are actually capped, and then photosensitive the layers are actually more sensitive and then producing dark electrons. I think the better, I think more dark electrons are actually being produced compared to the CCD material. Dark current becomes a real issue. So that actually the entire the instrument, okay, so including all these readout channels and then other the related the systems are all kept inside of the really cold chamber called cold dewar. Oftentimes that actually you are cooling this entire dewar by using liquid nitrogen into the minus 200 degrees Celsius. So imagine that actually you are doing this, the readout for the CCD, okay, in terms of that actually the exposure time versus the signal, okay, you basically just taking one single the observation at your own exposure and then just record, right? But because that actually infrared array allow the non-destructive readout, so what you can do is actually in the beginning of the exposure, you just take the readout maybe once, okay? So you take the measurement once in the beginning and once at the end. Then that difference is the accumulation of the photons during your exposure, right? So that difference actually over time clearly give you the count rate from your source. But oftentimes actually single measurement actually are subjected to the noise, variety of noise. So instead of actually this, the single, the measurement, okay, T and N, and this is the accumulation, okay? You take a series of measurement in the beginning, like this 3, and take the slope or maybe even median combining and to produce the initial level, okay? Then the measure at the near to the end, another 3 measurement. Then take the median combine of these 3, you get final. and final, and this is n initial. Instead of single measurement in the beginning and then at the end, you're actually making like this the certain number of measurement in the beginning and the end. You actually had the statistically more sound, and the noise is actually just smoothed out and then canceling out, so that actually you have nice robust measurement. And this multiple measurement in the beginning, multiple measurement at the end, is known as the Fowler sampling, that actually that mentioned in the earlier slide, Fowler. Okay, so and then other than this Fowler sampling, different one is actually during this readout. Okay, so this is the T and this is N. You basically just read out in a predefined interval. So along the exposure. So these the readouts, the strategy is actually known as the up the ramp sampling, okay, or uniform sampling. So this is actually really good because what something that actually strange things actually happening in the middle. Maybe electric potential is changed due to the sudden power the surge or a gray out, or maybe that actually one pixel was actually being hit by a cosmic ray. If the cosmic ray is hit, then what you see is actually gentle slope on that pixel. Then cosmic ray hit, then actually you see certain increase, certain jump, and then same slope from the before the cosmic ray hit, because you are actually receiving the constant the count rate from your source. So this type of sudden jump or the change due to the changing electronic environment, etc., can be all managed and then recovered through software, the subsequent data analysis. So this is actually really exploiting Fowler sampling, and then off the ramp sampling is really exploiting the non-destructive readout mode of infrared arrays. Okay, so as we can see, infrared array and then CCDs are actually similar in some way, but actually its operation is fundamentally different. So the infrared arrays, we need to actually worry about the elevated level of background due to the sky background or the dark current, but actually it's the readout operation is very different. Okay, so this wraps up the lecture on astronomical detector.